So let us start. Our next speaker, Leonid Plachta, he will be talking about some topological abstractions for strong coloring of uniform hypergraphs. Please.
Hello. I'd like to thank the organizers for giving the possibility to give me a talk. And the original problem which I consider here is more combinatorial problem, this vertex coloring of graphs and hypergraphs. This means that we, given for a given graph, we label the vertices with some colors in such a way that two adjacent vertices have different colors. So when considering the hypergraphs, the problem is formulated as following. What is hypergraphs? Hypergraph is the set consists of this base set and with some subsets which are called edges or hyper edges, but I will call edges. And what is a uniform hypergraph? Uniform hypergraph is can be defined as a simplicial complex in which each simplex of there is maximal dimension simplex and which each simplex of dimensional k, which is less than the maximal, is included in some simplex of maximal dimension. So we can think hypergraph as some union, correct union of simplex of the same dimension. For example, k dimension, and the idea, what is strong coloring of graph, hypergraph? The strong coloring of hypergraph is such a coloring, that each simplex of k simplex of the dimension k have different colors of all its vertices. So distinct vertices have distinct colors. So such labeling is strong coloring. There is weak coloring, and this differs from the strong coloring. There is another nuance. So in weak coloring, we only need that in each simplex there are at least two vertices with different colors. So the idea was not to consider this problem as combinatorial, as some problem to carry this problem in the area of algebraic topology. And the idea is to associate it with each uniform hypergraph some topological object with action of symmetric group. And the idea of considering such objects combinatorial as in the coloring problem as object of algebraic topology is not new, and it was used by many mathematicians. Now I indicated here some references on these subjects, and I will try only to describe what is my construction for passing with the pure combinatorial problem to the problem which arise in algebraic topology. So some definitions, first of all. So a map, the V H is denotes the vertices of hypergraph. This is base set, and we see that is H is simply the K, the subset consisting of K vertices, and the homomorphism is such a way that each is such a map of vertices such as each simplex, k-dimensional simplex is sending to k-dimensional simplexes, simplex. Our aim is to associate with each K uniform hypergraph H a cell complex BKS with an effective action of symmetric group SK. K is a parameter which responds for the dimension of hypergraph, and L is the number of colors in perspective. What is the main objective of this construction? What is strong? Oh, no, in this direction. So it is known that each hypergraph can be represented as generalized hypergraph of Kneser type. What does it mean? This means that given a hypergraph, we can represent it in the following way. We have the base set, we have some subsets and subfamily of subsets, and the subsets correspond to vertices, and there is a simplex, there is a hyper edge of dimension K if and only if the intersection of the corresponding subsets is empty set. And it is known that each hypergraph uniform K uniform hypergraph can be represented as the generalized Kneser hypergraph, as I mentioned before. And there is natural construction of such type, and I propose now some modification of this well-known construction. This construction differ from the known before in such a way that it is more economic and consists the subsets are smallest and in the original construction. What is we say that we also should to define what is a homomorphism of general as a Kneser hypergraphs. So we had homomorphism of hypergraphs, and parallelly we defined what is homomorphism of Kneser hypergraphs. So this is such assignment of the subsets of the base sets for the first hypergraph to the subsets of the base set of the second hypergraph in such a way that the following condition hold. Now, our construction has the following properties. That it is natural in the sense, and this is very important, that if we have some homomorphism of K uniform hypergraphs and send to this homomorphism, they correspond the homomorphism of general Kneser hypergraphs. Another, the second important thing, the second important point is that we can represent general Kneser hypergraph as some geometric objects. So this is description of such geometric interpretation. So if we have a base set, we consider subsets as simplexes based on these subsets. So the dimension of the biggest simplexes delta sub m minus 1 is just the number of the cardinality of the base set. And we consider the subsets which define the general Kneser hypergraph as subsimplex of this universal in our sense simplex. And to each hyperedge of dimension k, it corresponds the cell of such type, the cells of the Cartesian products of corresponding simplex. And these simplex have this property that the intersection, that they don't intersect the strong diagonal of Cartesian k-fold Cartesian products. And so this symmetric group SK acts on this cell complex. So we have cell complex DKS, and by permuting cells, so this is not free action but effective. But if we restrict ourselves to some cyclic subgroups, this action of no, for prime k, this action will be free. But it turns out that this construction, this correspondence between general Kneser hypergraphs and cell complex with G cell complex. I call G because no, this is with some action of symmetric group Sn. So this, unfortunately, this correspondence is not natural. So this means that if we have homomorphism of general Kneser hypergraph, no, we cannot assert that the corresponding map of, there is no good corresponding map of cell complexes. So we somewhat modified this construction so to obtain the situation where this construction, where this procedure leads to naturality of our construction. I don't focus here on the details of this construction because there is not so small time, but I only would like to formulate some results. So our construction of object, so this is not important, but that finally the map which we define for corresponding cell complex associated with generalized Nether hypergraph. No, this homomorphism descend to maps of cell complexes which are SK equivalent. What does it mean? This means that we now to understand what does it mean in our problem concerning our problem of coloring. We note that each coloring can be for example, L coloring, so coloring of hypergraph is L colors, can be considered as some homomorphism of hypergraphs and in particular as some homomorphism of generalized Nether's hypergraphs. So when we represent such hypergraphs as generalized Nether hypergraphs, so if we consider each coloring as homomorphism of K uniform Nether hypergraphs, so this means that basing on the previous results, that non-existence of SK equivalent map corresponding from domain space and target space is topological abstraction for existence of strong coloring of K uniform hypergraph. So to summarize this part of talk, I would like to formulate in other words. So starting from Kneser, starting with hypergraphs, one hypergraph, and asking whether this hypergraph can be colored with L colors, we pass to some homomorphism of corresponding hypergraphs. And the next step is to pass to corresponding generalized hypergraphs. And the next step is to pass to SK equivalent map of corresponding cell complex. So the non-existence of such SK equivalent map is if for some topological regions such equivalent map cannot exist. This means that original uniform K hypergraph cannot be colored with L colors. The nature of problem which arise here on this studying of topological project of the universal coloring space. So given for a given K, where the K is the dimension of edges of hypergraph, uniform, and L is the number of colors, is number of the colors. So this is the space BKL of C. The C is the corresponding system of set which defines the generalized Kneser hypergraph, and this BKLC is some testing space, topological testing space for coloring of for hypergraphs represented as generalized Kneser hypergraphs. I don't I cannot actually now I cannot no describe precisely what is the topology structure of the testing space, so each such testing space. But we can have some description of how it looks, and I want only to note that the similar object with which appears now when using all such objects as a universal color and space is topologically up to homotopy type, is most cases the weight product spheres, so of different dimension of the same dimension, and so now we have a good model. So it turns out that the existence of SK free action or effective action of the group symmetric group SK on some topological space, which have some connectivity, for example, M, it strongly depends what is the dimensional of the target space BKLC. So it is known from the Dold results. I recall, I indicated in the beginning of my talks that the main result on this subject is the Dold result, which asserts that in such situations the dimension of target space is biggest and at least the same as the connectivity of the initial CK initial topological space.
Leonia, excuse me, the time is out.
So okay, I only want to note that these results, this approach can be also can be applied to the problem of cyclic coloring of graphs embedded in surfaces, and we can formulate this problem generally in the language of coloring of L coloring of K uniform hypergraphs. So, but the main task now is to consider the topology, the abstractions which can appear when we consider such testing space and the study of topological product of such kind of testing space. Thank you very much for attention.
Thank you.